Okay, here's Trig Introduction Part 2, and we're going to talk about the sine and cosine functions. And we are going to look at tangent also, but we're looking at the basics of the unit circle and the relationship of right triangles. Again, I'm going over the introduction and going through the basics that I know you did last year, but it will help, trust me. Okay, the first thing we want to do is look at how the quadrants are named. And the quadrants are named and they go this way, which is counterclockwise, and we use Roman numerals 1, 2, 3, and 4. Okay? An angle in standard position is classified by the quadrant in which the terminal side lies. So the angle wherever it ends that's a second quadrant angle, or for first quadrant angle. The other thing I wanted you to see is when we look at the angles and how they're shown, if you go in a counterclockwise method, all the angles are positive. So this is 0, 90, 180. So this is counterclockwise. And that means the angles are considered positive angles in this direction. If I start here and going this way around, this is actually the clockwise method, and if I go this way, if I go clockwise, the angles are considered in a negative direction. Okay? So here we go, showing you the angles in the counterclockwise, and then this was in the clockwise. So this would be a negative angle, and that would be a positive angle. All right? Again, for review, coterminal angles, what are they? When a wheel continues a turn, it makes more than one rotation, thus generating angles which measure greater than 360. So you could have an angle that goes from here to here, but I could also start here, go all the way around the circle, and end here. As long as they use the same side, the terminating side, if they share this terminating side, they're called coterminal. This one here, I could go around several times and then go this direction. As long as they share that same side, they're considered coterminal. So an angle of 430 is coterminal with a 70 because 430 minus 70 is 360, and they end in the same spot. Again, this way too, an angle of 870 is coterminal with negative 210 because they end in the same spot. So basically here I wanted you to recall what coterminal angles are and how you can name them in multiple ways. At least two, but there's many, many more. Okay, let's review the unit circle. Okay, whoops. The unit circle basically has a radius of 1. And we always make it huge, and I always show kids it's really a little tiny circle in the middle of your graph paper. But if I have a radius of 1, if I go from here to here, my radius is of 1, and if I was actually graphing this, this would be the point 1, 0, 0, 1, negative 1, 0, and 0, negative 1. Okay? All the points on your graph, so if I was going to go over here and graph a point, we'll say in this quadrant here. Okay, so I'm going to graph a point. I'm going to graph this point P and call it XY. What you normally would do is go over X and up Y to plot that point. Okay? And this angle in here is considered, this angle in here is considered to be, we'll use a theta. So you can actually go over X, up Y to plot your point, or we can talk about what this angle is and the relationship is to come up with that point. So if this radius of this circle is 1, okay, we can come up with a lot of things that are happening here with the angle. So the point is XY, but it also can be, if I did the cosine of theta, so let's do this here, if I did the cosine of theta, which I know is adjacent over hypotenuse, this is my angle here. If I want adjacent, which is x, over my hypotenuse, which is 1, that shows you that the cosine of the angle, so if I take the cosine of the angle, it's the same thing as talking about the x value. So my point P could be written as cosine of theta in the x spot. Now the sine of theta, so if we were doing the sine of theta is opposite over hypotenuse, or O over H, okay? And that would be y over 1. So again, I can see now that the sine of theta equals y. So again, I can talk about going up y distance, or I can say, oh, if I know the angle, if I take the sine of it, it's the same. So all your points on your circle could be xy, or it's the same thing, the cosine of that angle and the sine of that angle. Okay? Also, if you look at this, we can see a Pythagorean identity going here. And we're going to talk about this again, but this is a history or backup, if you will, of what you've learned last year, is I can take and use the Pythagorean theorem here, because this is a right triangle, and say x squared plus y squared equals 1. And if I know x is cosine, I can say cosine of theta squared. And in trig, we always put the squared here, plus the sine of theta squared is going to equal 1. So now you have a Pythagorean identity with trig, and not just the sides, but with angles included also. Okay? Circle with a radius 1 and set it at the origin. That is our unit circle. Now, let's look at some unit circle degrees that we've learned last year to refresh our memory. So, if all our points are cosine, sine, and cosine are our x's, so here's all our points, cosine of theta, sine of theta, we can quickly go through, especially these quadrants here. So this is 0 degrees, this is 90 degrees, this is 180 degrees, this is 270 degrees, and this is 360 degrees. So you can actually go through and get values pretty quickly. So if I want to know the sine is 0, that would be the y value of this angle here of 0, and that is going to be 0. The cosine of 0 of this angle is going to be 1. The sine of 90 is the y value of 1, and the cosine is going to be 0, because that's my x value. The sine of 180 is the y value of this, so it's 0, and the cosine of this, because they're all cosine, is negative 1. And I know you can put these in your calculator, but it's so easy to be able to tell from this unit circle. So these are all the quadrant. The cosine of 270, if you come down, is going to be 0, and the sine of 270 is negative 1. Notice I didn't put 360 here because it's the same. I could have said it the same with 0, so that's not on here. So that's using the unit circle to come up with values. Now let's look at the definition of sine and cosine, which I have already alluded to, that you have your point xy, and now it's cosine and sine, and we also used SOHCAHTOA to find that. And we didn't talk about TOA, but this is tangent, and the tangent is opposite over adjacent. Okay, so if you're going to look at that, it's opposite over adjacent. And the other thing with tangent is, if you were looking at the values of the letters that we have, let's look at what we have. So I have, this is my x and this is my y. When you do tangent of this, so here if I look at it just here, okay, this is my x and this is my y with my sine. Tangent would be opposite over adjacent, or y over x. Or you can say it's sine theta over cosine theta. Okay? Now, the one thing I do want to show you about tangent is because tangent, usually people have to kind of memorize, because I know you remembered last year with all the values that all students take calculus to look for the signs. But I want to give you a little different perspective on tangent. Tangent is sine over cosine, or y over x, which is very similar to slope, which is delta y over delta x. So a lot of times I remember each quadrant here because I know the points here are positive, positive in my quadrants, negative, positive, negative, negative, and positive, negative. And so then when I look at this, I could go, okay, cosine, sine, cosine, sine. I know what cosine and sine are doing, or I can remember all students take calculus. But I want you to think about this. If tangent is similar to slope, watch what you do. If I had a line that went from here to here, you'd say that's a positive slope. Guess what? Tangent's positive here and here. If I had a line that went like this, you'd say, oh, that line has a negative slope. Well, guess what? Tangent's negative here and here in this quadrant. So I kind of remember sine and cosine, their signs by the points of what quadrants, knowing that it's cosine first, that's my x, and sine second. And then I think of tangent as lines. So I know tangent's positive here and here, negative here and here as lines. So that's just a shortcut that I thought would help. Okay? Now let's fill in the trig function values in each quadrant. Okay, so we're going to talk about quadrant. We're not going to do the values, but we're just going to do the signs. So I have quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Sines are y values, cosines are x values. Y divided by x is going to be my tangent. So quadrant 1, sines are positive and cosines are positive because the point is positive, positive. This is just a little backwards. So if I divide positive by positive, my tangent is positive in quadrant 1 as well. Quadrant 2, my sines are positive because they're my y values. My x's are negative. If I take a positive and divide it by a negative, I get a negative. Therefore, tangent is negative in quadrant 2. In quadrant 3, sine is negative and cosine is negative, but if I divide a negative by a negative, I get a positive. And in quadrant 4, my y's are negative, my x's are positive, and a negative divided by a positive is negative. So again, quadrants 2 and 4 are negative, and 1 and 3 are positive, just like the slope of the line I showed you. All right, next. What if the unit circle is not a unit circle? Okay, excuse me, what if a circle is not a unit circle? So basically, I know the x's are my cosines, and that equals my radius as of 1 over 1. If I cross multiply this, my x's are the cosine as my radius to 1. If I were to cross multiply, I'd see that my x's are my radius times my cosine of theta, and my y's are the radius. So your x's are still cosine, your y's are still sine, but you have to multiply it by the radius if the radius is greater than 1. So for example, I've got 3 points here that we can look at. I have point A, which is at a 150-degree angle. So I want to know what this point is. So they tell us the radius of this circle is 6. So this is 6 here. If it was a unit circle, I would just say, oh, it's cosine of 150, sine of 150. But since it's 6 away, really my point for A is going to be 6 cosine theta, 6 sine theta. And if I were to put that in my calculator, I would get negative 0.5, 0.19, and 3, which kind of makes me happy because negative 5.19, well, actually 5.2, 3 is a negative positive, so that's the point here. If I look at point B here, that angle there, they said was 15 degrees more, so that's really 165. Or excuse me, 195, because it's come all the way over here, right? So when I do that, I have to do the 6, because it's 15 past 180, okay? So point B, excuse me, is going to be 6 the cosine of 195 degrees, and 6 the sine of 190 degrees. And when I put that in my calculator, I get point B to be negative 5.8 comma negative 1.6, which makes me happy because it should be negative there. And then for point C, it's got 40 degrees more than 270, so we're talking 310. So this angle, this point C is actually, I'll put it underneath here, point C is actually 6 times the cosine of 310 and 6 times the sine of 310. And my point comes out to be 3.9 comma negative 4.6, which is positive negative like it should be. So that's if your unit circle is larger, so it's not a unit circle anymore, but it has a different radius other than 1. Okay, let's talk about some exact values and where they come from. So I took a square here. I took the square and I basically cut it in half so that I have this triangle here that has a 45, 45, 90 degree angle. Okay? Now, because you're going to have to learn the table of values, I want to show you where they come from. And we're going to use SOHCAHTOA again, so you guys see where all of these values come from. And I'm going to show you this. So if I did the cosine of angle A, which is 45 degrees, okay, it's adjacent over hypotenuse, or radical 2 over 2. And you're like, well, where'd you get the radical 2? Well, if this is 2 here, and I need to find what these sides are going to be, all right, I would have to say, okay, x squared plus x squared has to equal 2 squared. I have 2x squared equals 4. X squared equals 2. Take the square root of that. X is radical 2. So this is a radical 2 here, and this is a radical 2 here. Okay? Now, having done that, now you can find the rest of them. If I wanted to find, and so the cosine of A, which is 45, so I can change this to 45 now, is radical 2 over 2. The sine of 45, which is opposite over hypotenuse, is still, if I did the sine of A, so this is A, and go as opposite over hypotenuse, is going to be also radical 2 over 2. And the tangent of 45, and we're looking from point A's perspective, is also going to be opposite over adjacent, or radical 2 over radical 2, or 1. So here's some of the values that you have for 45. They come from a a rect square that is cut in half. All right. Now here I have an equilateral triangle that has 2 on all sides. When I split it down the middle, this is 1, and so basically we're just going to look at one of these, so we're not going to look at the bottom at all. Okay. So what I want you to do is, I don't know where this came from. Cancel. Okay. Is what I want to do here is show you where these angles come from. So if I want to do the cosine of 30 degrees, the sine of 30 degrees, and the tangent of 30 degrees, I'm going to use that triangle. So this is 1 and this is a 2, and we have to find this side. So if I did 1 squared plus, we'll say x squared, has to equal 2 squared. So when I go through do the Pythagorean theorem, I get x squared equals 4 minus 1, or 3, or x is going to equal radical 3. Okay, so that means this side of my triangle here is radical 3. So just look at one of the sides when we do this, and then we're going to do the cosine of 60 degrees, the sine of 60 degrees, and the tangent of 60. So this will cover our main angles that we have to do in quadrant 1. So the cosine of 30 is adjacent over hypotenuse, so that is radical 3 over 2. The sine of 30 is opposite over hypotenuse, or 1/2. And the tangent is opposite over adjacent, is 1 over radical 3. But we can't leave it that way. We have to rationalize it. So it's radical 3 over 3. The cosine of 60, if I'm over here, is going to be adjacent over hypotenuse, 1/2. The sine of 60 is opposite over hypotenuse, or radical 3 over 2. And the tangent is opposite over adjacent, or radical 3. So all these numbers should look familiar to you because we learned them last year in the table. I just wanted to show you where they came from. They came from these two special, one's from a square and one's from an equilateral triangle. Now, if we find the exact values of this one here, you're going to see a pattern happening. So let's look at it. This is, we're going to use theta 1, theta 1, theta 1. I forgot to put it here, and these are theta 2's. So watch what we do. If we did the sine of theta 1, so we're here, and right here this is 3, 4, and 5. If we did the sine of this would be opposite over hypotenuse, or 4/5. The cosine is going to be adjacent over hypotenuse, or 3/5. And the tangent is going to be opposite over adjacent, or 4/3. Now watch what happens when I do the other angle in the triangle, and it's really interesting. If I did theta 2 here, so I'm looking here, if I did the sine of this, it'd be opposite over hypotenuse, or it'd be 3/5. See how the sine of theta 2 is the same as the cosine of theta 1? And look at cosine of theta 2, you guessed it, is going to be 4/5, which is going to be the sine of theta 1. And the tangent of theta 2 is opposite over adjacent, or 3/4, which is this reversed. So it's like a pattern that we have with this. Okay, that ends the Trig Intro Part 2.